Okay. Um, Now we can talk about a couple of remarks about the concepts that we are talking. So, remarks. Um, when we look at these initial examples of new generalized methods of convergence, we can see that they have some common properties which are crucial to arrive at a formal definition of a summability method. So, firstly, uh, uh, we choose um, uh, a standard notion of convergence on which the new convergence method is based. So first we need to have a well-known or ordinary or standard convergence to base our new generalized convergence on it. In our initial examples, we took ordinary invergence of sequences as the standard convergence here. Most of the time we use the ordinary convergence of sequences to build a new method on. And secondly, we define a map, the definition of the map by connecting to the standard convergence. So first we take a standard concept of convergence, then we define the map by connecting it to the standard convergence. So there has to be a connection between our new method and the ordinary convergence or the standard convergence that we want to use. And third, the set of all sequences on which the new notion of convergence is applicable. I mean, we are interested in finding those subsets of sequences that can be mapped into a new limit under this new method. So we are interested in three main things when building a new summability method. On the basis of these three principles, we can formulate the definition of summability method. Okay. Formulation, summability method. Okay, a summability method is in fact a summability method V is a triple cap V and V and limit functional. Consisting of a map V from D into M, where D is a subset of the space of all sequences and M is a set of sequences such that there exists a standard a standard limit functional f defined on n where n is a non-empty subset of M. So first, it has, we say that a summability method V is a triple consisting of three things. The first is a map defined on D into M, where D is a subset of all sequence space, and M is a set of sequences. M does not have to be sequence space here. It's enough for it. It's enough to be a set of sequences such that, but M has to have a non-empty subset of cap n, where there is a standard limit functional f, which is defined on this n into real numbers. Secondly, the domain cap n v, which is the inverse of cap n under v of the summability method v, and the summability and the new summability functional v limit of, which is actually the restriction of the union of f and v into nv, from nv into real numbers. So here I don't want it to look confusing. This nv is, and this n is the same thing. Okay, it is the same thing. I just wanted to emphasize n is the main domain of the map V that we are interested. Okay, so there are three content for each summability method. One, a map. Second, the domain of the map. And third, the new summability functional, the new limit of, the new generalized limit of sequences. We will be using these three whenever we talk about a summability method. So we say that each x in NV is called V summable to V limit of x So I will give you a couple of examples. So let M be W, omega, and be convergence sequences, and F be ordinary convergence of sequences. So as I mentioned in the beginning of formulation of summability method, we say that we will need three main things. First, a set of sequences which we take as the set of all sequences here, and a non-empty subset of M, which is omega, as the set of all convergence sequences, and a standard limit functional that we are all familiar with. Here we take the ordinary limit of convergence of sequences as the standard limit that on which we base new methods on. So first example is identity map, putting V I omega from omega into omega which is basically identity map. The identity map. Here CV is C, and the new method that the summability method that we are interested is actually the standard method itself. V limit of x is limit of x. So this example says that the standard convergence of sequences can be considered as a summability method. Therefore, identity map C and standard limit functional is a summability method which is ordinary convergence of sequences. Second example is the zero map. If V from omega into itself is the zero map, then CV is exactly omega, and V limit is the union of ordinary limit operator and V is the zero functional. So V, the triple V, omega, and V limit is a summability method that sums each this is important here, that sums each sequence to zero. So with ordinary sense, we know that there are infinitely many sequences in omega that are not convergent. But with this very fundamental, very basic example, if we take zero functional and zero map, we can sum every sequence to a limit which is zero. First, we take any sequence X and map it into omega as the zero sequence. Then we know that zero sequence is a null sequence with ordinary convergence, and the limit of the ordinary limit of it can be taken as the V limit of this method. So in that way we can assign every sequence a limit. So this is a non-trivial example. This one is a trivial example. I mean, we just said that we just said that ordinary convergence can be considered as a summability method. That's why it is a trivial one. This is a basic one, but at the same time a non-trivial one. But third and fourth examples are much more interesting. We talked about Z1 over 2, C Z1 over 2, and Z1 over 2 limit. This triple is a summability method which is called the Zyver method. This is the name of the German mathematician who came up with this method. of order 1 over 2. And lastly, the triple C1, C cap C1 and C1 limit functional, the Cesaro method is a summability method. So when we look at these 4 examples, we can see that they the map that they all have has they all have can be expressed by a matrix method. I'm going to explain it to you. Okay. Yes, exactly. Otherwise, we cannot say that such methods create a new sequence space. Yeah, they have to be linear. I mean, for all those 4 methods, I mean, this one is a trivial one, and this is just 0 map, so they are clear. But this 3rd and 4th method also linear operators. So in that way, we can say that the sets of sequences that are summable under these methods create a sequence space. So if we research on a new type of summability method, we generally, mathematicians, want it to be based on linear operators, so that we can have a new sequence space. So mathematicians who are expert on this area always try to find a new sequence space with a new summability method. So the operators that we are studying with are expected to be linear. If they are not linear, we cannot have a linear. We cannot have a sequence space. These new summability methods. Here, you mean here? No. It is linear. I guess I forgot to mention here. Yeah. Yeah. The V limit is linear. Yes. Okay. Constant. Yes, exactly. Yeah, that's true. Constant ones, yeah. No, I guess so. Yes, I don't think if it is not constant, I don't think so. We can assign each sequence a limit. Yeah. I mean, otherwise, I mean, when we try to have a new summability method, generally speaking, we always want that there must be some sequences which are not summable under this summability method as well. When we come up with a new idea, we most of the time expect to give an example that hold this new method. But it is also important to come up with an example that are not summable under this method as well. So honestly, the constant operators are not so interesting for us. It is so obvious, but they can be considered as initial, as basic examples of the concepts. That's why most of the time we start with such initial examples. But the more we advance, I will be sharing with you some other types of summability methods, which are pretty different. Yeah. So we by these examples we can see that the methods, especially the maps Z1 over 2 or C1 can be represented by an infinite matrix. So this makes us unable to give a method which is called matrix method. Okay. So definition. Matrix method. Let infinite matrix A and K be given as follows. So this is an infinite matrix which infinitely many with infinitely many columns and infinitely many rows with A and K is a real number for all n and K from natural numbers. be an infinite matrix, and let omega A is the set of all sequences from omega such that AX, which is infinite series of nk times xk, exists. That is the series is convergent for all n. So this set is called the application domain of A. Yeah. And CA consists of sequences such that the image of X under A is in convergent sequences. And this set is called domain of A. Of A. Okay. So the limit functional, I mean the new type of limit is defined as follows. A limit of X, which is the limit of which is under the union of limit and A, sorry, is defined on CA into real numbers such that X goes to A limit of X as the limit, the ordinary limit of AX. It is so clear that I mean one can wonder why we do not define this limit functional on omega A instead of CA. If we had put omega A instead of CA here, then this relation cannot be a function. It cannot be well defined because we cannot make sure that every sequence from omega A from here goes into a sequence which is convergent with ordinary sense. That's why we take CA, which is the domain of A, as the main domain set of this limit functional. This is crucial here. Yeah. So the summability method A, CA and A limit, A for short, is called a matrix method. Yes. Okay. I guess this is a good place to stop today. We can continue tomorrow. If you have any question, you can freely ask though. About this? Okay. At the end, what? A, C, A. Yeah, this one, no, I mean, the map is A itself. The map is here A. This one is the map. This is the domain of it, CA. And this is the limit functional. Okay. Yeah. Actually, we were ending the class. Yeah. Okay. Oh, really? Okay, no problem. Okay.